stuff because it's showing us what's happening on both sides of the y-axis. So you throw a -2 in, you get 7. Okay. If you throw -1 in, you get 4. If you throw 0 in, you get. If you throw 1 in, you get. And if you put 2 in, you get. Well, that's convenient, isn't it? Hey, it should be because it's symmetrical and it's a parabola. Who would have thunk it? I know. Hold all of your applause. So when we did this, then you would have some ordered pairs to plot. So take a second and plot the ordered pairs. Let's see, -2 and 7. -1 and 4. Then it looks kind of like this. Do you agree with me on that? Now, the next step, it said that I asked you guys to, how I worded it, take the ordered pairs from above and flip-flop the x and y values and call them x prime, y prime. What does it mean to flip-flop? Switch them. Okay, switch them. So basically what I want you to do is take these values here. Oops, that didn't work as well as I was hoping. Flip-flop the x and y values. So now, that's not going to work. 11th hour was asking questions about what do you do when you have different variables, and we kind of said, well, you can only use 26 letters. I'm like, well, no, you can technically use everything. So, have you guys ever seen this idea of what's called x, little tick mark there? It's called x prime or y prime. What that's denoting is that we're just switching the values around. Okay? It's just a common way of rewriting stuff. So when I flip-flop those values, we have -2, -1, 0, 1, and 2, 7, 4, 3, 4, and 7. Does that sound right? Okay. Now, when I replot these, 7, -2, 4, -1. Yeah, put them on the same graph, please. And then the last thing I asked you to do was plot the line y equals x. When I plot the line y equals x, what's the y-intercept? 0, what's the slope? 1. Good morning. How are you? The line y equals x. Now, when you look at these two, do you notice anything? What does it look like? Triangles are the parabolas. Is that what you're getting at? Yeah, and that's kind of the idea here. If you look at it, and it's kind of hard to see that. It's kind of hard. I tried to figure out and find some sort of a graph that would be easy to work with. Like Tom was saying, if I folded them in, they're almost symmetrical. They're symmetrical not about themselves, but they're symmetrical along that line, y equals x. Okay? They're symmetrical about that line y equals x. But the reason why they look like that is because these two graphs, the one I graphed in black and the one I graphed in red, they're inverses of one another. Okay? They're inverses of one another. Basically what that means is, well, there's a whole bunch of definitions here. So what we're looking at today are exactly what we're talking about, are inverse functions. Right? And in order for functions to be inverses of one about the line y equals x. And we're going to go into a whole bunch of definition off this here in a second. Right? So as we get going into this, you'll notice what we did to show that they were inverses was that we just flip-flopped the x and the y values. That's how we can create an inverse when you're using tables. Just flip-flop the x and y. Right? But there's also easier ways of doing so. The other reason why we talk about inverses now is because when we get into exponential functions next week, we'll start talking about exponential functions. We'll talk about what are called logarithmic functions. We have to understand how inverses work to work with those guys as well. So inverses, the graph of an inverse relation is the reflection of a graph of the original relation about the line y equals x. Basically, again, that just means these these points, these 2 points here, are equidistant to the line y equals x. As you go through your ordered pairs, these two values are perfectly the same distance. These two guys, as you figure out all these distances, those distances between, the line y equals x is like the midpoint of those two distances all throughout. They're perpendicular to through it. Okay? That reflection. What's that? You said you did something like that in geometry? Oh. Yeah, it depends if you guys had time or not. There are some, if you guys had time last year, you did some reflection stuff. If you did, great. If you did, it's not the end of the world. Okay? It's one of those sections that we kind of leave off if we run out of time. So let's take this, and we're going to find the inverse. To find an inverse, it's going to be really, really, really difficult. Try and stick with me. Switch x and y. Solve for y. Switch x and y and solve for y. That's all you do. Okay. So if I switch x and y, now I got to get y by itself. If I get y by itself, what do you have to do first? Add the 4, and then divide everything by 2. Those two functions are inverses of one another. And a lot of times, to show that it's an inverse, they'll put a little tick mark next to it. That's fine. Y prime and y are inverses of one another. Again, the reason why this works, because all we're doing is we're flip-flopping the x and y values. We're going to resolve for y. Okay. Algebraically, to show that something is an inverse, oops, let me move this down here real quick. So we have y. Would you guys be okay if could you leave it like that? X plus 2 all over 4, or if you wanted to, could you write 1/2 x plus 2? Is that okay? It's totally up to you how you want to rewrite it. Sometimes if you write it all over 2 or however the fraction might wind up being, it's fine. It's not a big deal. Okay. Now, in order to show that these two are in fact inverses, what we're going to do is you substitute in one for the other. Here's what I mean. If I take 2 and I throw in simplify that. And then do the same thing. Watch what happens. When you simplify those, watch what you're left with. If I distribute in that 2, what's 2 times 1/2? 1. 2 times 2 is, so I get x, don't I? Do the same thing on the other side. What's half of 2? 1. Half of -4. And what do you get? X. In order for you to show or to verify that two functions are I'm going to say functions, but two equations are inverses of one another, you just substitute in one to the other, like we were doing composite stuff last week. And if you get x for both of them, they're inverses. It's that straightforward. Okay. Flip-flop x and y, resolve it. That's how you get an inverse. In order to show that they're inverses, put one in for the other. You should always buy out equal x. What's wrong? You don't have to apologize. Is the rain going? Are all obstacles out of your way? Thank you. No, you can see clearly now because the rain is gone. Is it going to be a bright, sunshiny day? It's song lyrics.
Oh my
God. I'm sorry. Why are you complaining?
Okay, so this weekend has been the longest weekend of my life. Yesterday I was only had 4 hours of sleep because I had a softball game till 11 p.m. Then I wake up at 5
I really
a.m.
want to know the whole story.
And I wore my sleep next inside out. And I didn't know until we were playing volleyball. And I'm so embarrassed. My tags are sticking out and everything. It's the most embarrassing moment of my life. And everyone knows it's so embarrassing.
I don't know. I got Scotch tape on the table.
I don't care. It's so embarrassing.
Anyway,
Everyone already knows.
so like I was just saying a second ago, what we just did was this step here. Last week we talked about what was called composite of functions. We took two functions and substituted in for one another, f of g of x or g of f of x, things like that. That's basically what we just did. Whenever you simplify them and you get x for both of them, that means those two functions are inverse. That's all that means. When you throw something in for the other, and it works. Okay? It is really, really, really simple. Oh, we just did this one. Now, let's find the inverse of this and talk about why there is a restriction. So we want to find the inverse of this, and before we do that, excuse me, what does the graph x squared look like? It's a parabola, right? It's up like a cup. Be okay with that? It's a parabola that's up like a cup. Now, 10 minutes ago, we did a graph that was a parabola, but it had an added, like a k value to it. We moved it. Remember that? We moved it up a little bit. So go back and look at that graph real quick. And before we got into all of these lines here, we graphed that first parabola, x squared plus 3. Now, when we did that, we found its inverse. We flip-flopped the x and y values, and we moved it over. Now, was the inverse a function? No. Why? Yeah, it doesn't pass that vertical line test. Okay, it doesn't pass that vertical line test. So that means that if the original function doesn't pass the horizontal line test, its inverse won't pass the vertical line test. All right. See where all that goes? So now going back to the idea here of why do you think they put the domain restriction on this? Right. So now if you put the domain restriction on it, you're only looking at positive values. Oops. which means when you do your inverse, you're only looking at positive values. Here, again, think of it this way. So if we go to find the inverse here right off the bat, if I'm looking at just straight flip-flop x and y, that means I'm going to get x equals y squared. Everybody okay with that? All I'm doing is flip-flopping x and y. Remember, f of x means the same idea as y does. Okay? So I'm flip-flopping x and y here. Solve for y, what do I have to do? Square root. But remember, it wants only positive values of x. So I'm just going to do the square root of x is going to equal y. Okay? Now, think about what that graph looked like. If I have if we just pick really easy values to work with, if I pick for the original one, let's just pick 1, 4, we'll do 1, 2, 3, and we'll probably put 0 in there, sorry. Let's do 0, 1, 2, and 3. What's 0 squared? 0. Okay. What's 1 squared? 1. 2 squared. 3 squared. So it's doing that. Okay. Now, if I turn it around and think of the other graph, I'm going to pick different numbers for my x values. Instead of 1, 2, and 3, I'm going to use 0, 1, then I'm going to use 4 and 9. Reason being that way it fits. Because I want to pick values that are going to be easy to work with. Okay, does that make sense? So if I'm doing that, actually, let me just put a regular graph on here so you can see. So we have 0, 1, 1, 2, 4, 3, 9. So there was our first one. What's the square root of 0? 0. What's the square root of 1? 1. What's the square root of 4? What's the square root of 9? 3. Oops. You get those two curves. And they're inverses of one another because if you throw the line y equals x, they're symmetrical on that line y equals x. And the reason why they put that domain restriction on it is because now does the line x squared when x is greater than or equal to 0 pass the horizontal line test? Yeah, which means the graph of the square root of x being just positive value also passes that vertical line. So if it passes the horizontal, it'll pass the vertical, which means that they're both functions. And that's where this goes. Again, you're just flip-flopping x and y and resolving for y. Does it change with higher degree? No. Because how do you undo cubing? You cube root. How do you undo 50? You fifth rooting. The same idea. Okay. You're close-ish. Okay. So let's do this one. 1/2 x cubed minus 2. What does the graph of x cubed look like? Do you remember? You have tails? Yeah. Your tails, you're down up, aren't you? Our a value here for the x cubed is positive, so it's going to be down up. What does that -2 do to the graph then? Yeah, it just shifts it down. Very good. It's just shifting it down. So if you think about polynomials and stuff from back in the day, well, October, November-ish, when you did that, like you were just saying, it kind of looks like this. Is that a function? Yes. Does that pass the horizontal line test? So when I do the inverse of it, will it pass the vertical line test? Yeah, so will the inverse of this be a function? Yeah. So let's figure out, how do you find the inverse of this? Well, the inverse of this, remember, first thing you do is you flip-flop x and y. X equals 1/2 y cubed minus 2. Okay. What do you do first? Add 2. Yep. Add 2. Now what? Multiply everything by 2. Very good. And then lastly, what was that? Cube root it. Okay. Now we had those two values. Take your calculator out, put them in your y equals. Okay, take your calculator out, put them in your two separate y equals. Get my calculator out. I don't care about this, just close it. All right, what were they? What was the first one? Bless you. When you're putting stuff in the calculator quickly, do you have to make a fraction for 1/2 or keep it 0.2, 0.5? Yeah. The only difference is going to happen when you, if you had to look at the table would go to decimal format versus fraction format. Was it minus 2? Thank you. And then the other one was the. You guys know how to make the cube root, right? Math. Hit the math button. And then it was f. Oh, it's 2x underneath the radical, and that was all it was. Okay. So if you go to the graph, there's your first one, and there's your second one. Yeah. And then, for fun, put y equals x. Everything's symmetrical about the line y equals x. It's a very clean looking graph as you go through. Okay. Inverses are fairly simple to work with. Okay. It's really just a matter of substituting in one for the other to verify that they equal x, or flip-flopping x and y. We probably won't be doing much graphing with this, because since we did wind up with this whole movie thing this Thursday, we just don't have time to do the graphing in this section, which is fine. It actually works out rather nicely, because then next week when we start exponential functions, we always started by graphing them. So we'll start by graphing square roots, cube roots, stuff like that, and then we'll go into the exponential, and we'll just do a whole little mini unit on the graphing before we get into all the word problem stuff. Oops. Take a second, verify that these two are inverses of one another. Remember, in order to show that they are inverses of one another, that means that f of g of x has to equal x, and g of f of x also has to equal x. If that works, then they are in fact inverses. What has those stuff? don't lose them. If you lose them, you don't get to go.
And pay attention to what period it says that you guys are going.
I think the.
Orange is end of the day, yellow is.
I thought it was the other way around. Okay, so I thinking backwards. At first count, when we were doing it, the list that we had last week was looking at 1 and 2 this time.
I get it.
You don't have to. I don't know. You don't have to. So then does that mean that 11 hours won't fix something? I don't get it. Yeah. I looked at that list and I thought I had it done right.
Oh, test is still Friday.
Yeah. Yeah. So that's the case. I will do graph. So again, when you do this, remember what this means. It means you start with the g of x equation, you write it down, and you surround it with the f equation. So you start with the g equation, the x to the third all over 2. Surround that, the other. So now when you have power to power, multiply. So what's 1/3 times 3? 1, and then 2 to the third power is 8. So this gives you 8x over 8, otherwise known as x. Okay. Do the same thing with, bless you, do the same thing with the other one. Start with the f of x equation, which is the 8x cubed. And now you surround it with the g of x equation. 8 to the 1/3 power means cube root of 8, which is 2. X to the third power to the 1/3 power is just x. So you get 2x over 2, otherwise known as x. Hey, did both of those equal x? Yes, therefore they are inverses. Well, in this case, you get lucky because yes, they are both functions because the cube is there. All right. You have to be careful with domain restriction ones, where they usually make it set up so that it works out. I think that's really all you need to worry about. Of course. Yeah.
So embarrassing.
All right there. Don't hurt yourself.
Everyone saw it.
Do it.
Why do you shave off your eyebrows?
Do those, please. 426.
That's a lot.
Really?
Yeah. It's like 15 probably.
No. Yeah. You're so close.
Right?
You know what? I will say that I've done some dumb stuff in my life as well. It's about what, 6th, 7th grade when you guys first learn about like Bunsen burners and things like that. So